As we continue our discussion of the work energy theorem, the next part of this is called work done by friction. Friction is a different animal. So let's go back to the problem with the car that we did in a two-step process. So we said at the beginning right here, we had 211,750 joules of energy. The engine does 611,000 or 635,750 joules of work right there to give us 847,000 joules of energy at 44 meters per second. That's cool. But now we come to a stop. How much energy do we now have? Zero. You had $847,000. What happened? You spent it all. Where did it go? Just like money, it's not destroyed. It went somewhere, and you actually got something useful out of it. So there was work being done. Energy is changing forms, and it's changing amounts right here. We had this much, and we had this much. When energy is changing, work is being done. The question is, what is doing the work in this case? Well, the engine did the work here. The engine is what does the work to convert chemical energy into heat energy and kinetic energy. What's doing the work to stop your car here? Well, it's fairly easy to say that that work is done not by the engine. The engine doesn't do the work, but the brakes. The brakes do the work right here, and specifically the force, not of friction, but friction. The force of friction does the work in order to bring your car to a stop. Okay, so that's the force that does the work, and it does negative 847,000 joules of work. It takes $847,000 out of the bank. But where does that energy go is so important. When you spend money at the store, you know where that money is now. It's in the hands of the store clerk. But where did this energy go? Let me show you a picture. These are called brake rotors. Those of you that know a little bit about a car, you'll know this. If you don't, go and look at your car just on the inside of the wheel, and you'll see this shiny silver disc. That silver disc is called the brake disc or the brake rotor. It rotates with your wheel, and there are things called brake pads that press on either side. So there's one of these on either side. So you'd have a pad here, the rotor in the middle, and another pad on the other side. And the pads press on the rotor as it's rotating when you hit the brakes, and that's what causes your car to come to a stop. This is a new one. This is an old one. And the old one, you might be able to tell, is really, there's a really big ridge on the outside of it because those brake pads have been rubbing and rubbing and rubbing on the inside of this. In the picture I just showed you, here's an old brake pad and here's a brand new one. These are made of metal. This metal has literally been burned off. And I don't recommend doing this. Maybe you already have in the past. If you drive around for about 20 or 30 minutes, put the car in park, and then if you've ever touched this brake rotor, you'll know that it gets extremely, extremely hot. And the question is, where does that heat come from? And that question relates to what we were just talking about a minute ago. It relates to this concept of the brakes. Where did the kinetic energy go? Where did the money go? Well, the brakes get really hot. If you rub your hands together, do this, rub your hands together like this and do it for a long time, you'll notice your hands getting warm because friction most of the time creates heat. And that is exactly where the energy went. Really important point here, that the energy isn't destroyed. It went somewhere. Kinetic energy was converted to heat energy by friction in the brakes. It heats up the brake pads. It heats up the brake rotors, a lot of the components around the brakes. But if you could accurately measure all of the heat energy in all of those parts after you come to a stop, you would come up with exactly 847,000 joules because there's that amount of, this is where the energy came from, that's where it is now. And the question is, where does the heat go now? It cannot cycle back to your engine. That can't happen. Heat, once it goes to your brakes and to your brake pads, is actually just dissipated to the environment. It's still there, and what exactly it does at this point is kind of up for debate. but the heat is now just dissipated to the environment, but it isn't destroyed. So I just want you to back up and understand this full picture. This is a really important sort of practical thing I want you to understand from this course, is just general energy transformations in your everyday life. That when you buy gas and put it in your car, your money purchases chemical energy that's going to go to your engine and create heat energy, and that heat energy will be converted to kinetic energy. By the way, all these energy transformations are not complete. They're not perfect. You lose heat in this process. You lose some heat in this process. So there's energy constantly decreasing, and we'll talk about why in another part of the class. But that kinetic energy that your car has, that's what you're interested in because you want your car to move. But then when you hit the brakes and come to a stop, literally you are burning the money that you spent here. You're burning it away in heating up the brake pads. And now hopefully you can see why when you're driving down University, for instance, any road where there's a lot of stoplights, if you gun it from a stop, it isn't very useful to do that because you're using more of this, which creates more of this and more of this, which creates more of this, but you're only going to come to the next stoplight, which means you're going to lose the same amount of energy that you just created from the gas. And so it's important to understand that it's impossible to stop this process. You constantly have to fill up your car because your money is leaving your car in the form of heat in the brake pads. But the slower you can make that process happen, the better, and the less money you're going to spend in the long run. So here's the point. When we talk about work done by friction, we need to understand that if we talk about gravitational potential energy, that's related to height, remember, potential energy is always produced by work. You can't give that bowling ball potential energy without doing work in the middle. You can't give your own body potential energy at the top without doing work in the middle. Potential energy is always produced by work, but work doesn't always produce potential energy. Hint, hint, in this case, you will have a question that says, what happened to the kinetic energy the car had? And many people will say, well, it became potential energy because we're so used to saying kinetic energy gets converted to potential energy. It doesn't. Your car doesn't gain height as it's stopping. So the kinetic energy does not get converted to potential energy. There is work being done, but that work in this case doesn't produce potential energy. All forces can do mechanical work, and you need to understand that when we use the word mechanical, mechanical just means movement or moving, right? So all forces can do mechanical work because they change the motion of an object. They change the amount of kinetic energy or moving energy an object has. Friction can also do that, but it can only do negative work. Negative work because friction cannot give your car energy. Friction can't make your car go faster here. Friction can only take energy away. It can only do a withdraw. Okay? So friction does negative work. It still does work because it changes the kinetic energy of an object, but it can only do negative work. Does this mean friction destroys the energy? Destroys is a key word. Destroys means it goes away forever and it's gone. The answer is no, because energy cannot be destroyed. Friction is the only force that doesn't increase an object's kinetic energy. It decreases it because it converts kinetic energy into heat. And that is a really important point to know. Okay, so as we talk about work done by friction, we need to understand how to work problems that involve work done by friction. So I'm going to talk about some concepts related to this as we deal with these problems. So this first example, you have a kid going down a slide. Let's draw it. How about that? Ladder up the slide, slide at the top. There you go. Pretty simple. At the top, I'm going to say this is the initial energy state. Here's the final energy state. What kind of energy is going on at those locations? Well, at the top, you have height, but no movement yet. So we got potential energy here. At the bottom, all your height has been converted to kinetic energy, so we got kinetic energy going on. Sliding down a slide. 850 joules of potential energy at the top, that's what they tell us. 775 joules of kinetic energy at the bottom. And then it says how much work was done by friction. In other words, the question might say this, but it's the same question. How much energy was lost to heat generated by friction? Same question. So here's the deal. You need to understand that on this slide, if there is no friction, here's the deal. As we said before, rub your hands together. Friction creates heat. So there's another thing that's going on in any problem involving friction is that as you're going down this slide, heat energy is also being released. Your butt is getting heated up. The slide itself is heating up because of friction. If there's no friction in this system, then there's no heat going on. And this is energy. This is heat energy, right? If there's no friction, we can't get that heat energy. And if that's the case, then the energy is the same at the top and the bottom. Energy is the same from the top to the bottom. If there's no friction, energy stays the same. We see that our energy is not the same. Therefore, I know there was friction on the slide to take some of that energy, some of that mechanical energy away. So, how much work was done? We're going to start with the same equation. W equals EF minus EI equals FD. Don't need this one on this time. We're going to use this. Now, what's different about this problem is they actually gave us the amount of energy. I know that's potential energy. I know that's kinetic energy. But I don't have to put the equations in here to find them because they already gave me the actual amount. So all I have to do is say, okay, final energy is right here. That was kinetic energy. It's 775 joules. The initial energy was potential. That's 850 joules. In other words, all I'm doing is subtracting them. In terms of money, you had 850 bucks. At the end of the day, you have $775. What happened? Well, you lost some. All we're doing is figuring out how much money was lost. 775 minus 850 gives us negative 75. Again, negative work means energy is removed. Friction is removing 75 joules of heat energy. Again, if there's no friction, this is 850 and this is 850. But because we do have friction, heat is being lost. Heat energy is being lost. Let's look at a second example. On this one, we have a girl that is sledding down a hill. We're given her mass. We're given the height of the hill. Okay? Let's draw it. Initial energy at the top. EF at the bottom. At the top, the hill is 5 meters high. And because of that height, she has only potential energy at the top, not moving yet. At the bottom, she's moving and she cannot go down any farther. She has no more height, so she has kinetic energy down there. During the slide, how much work was done by friction? So again, because friction is going on, I know that there's also heat energy being lost here, and I want to know how much heat energy is being lost. How much of that work is done by friction. Start out this way again. And also, like before, though that won't always be the case, don't need FD because they don't give us the force and the distance and they don't ask for it. Now, some people will say, wait, they gave us a distance. That is a distance, but it's really the height that we're going to use to calculate potential energy. And there is no force here. There's no force given in this problem, so we can't do this. All right, so here we go. The next line, I know that the final energy is kinetic energy, and they don't give me that amount of energy in this problem, so I have to calculate it using the formula, which is mv squared over 2. The initial energy is potential energy. That's just a different formula. Potential energy, remember, is mgh. It was mv squared, 1/2 mv squared's brother. You might remember that. Kind of a joke I made. But there we go. So that's how we're going to calculate our energies. Now we can plug in numbers. Her mass is 20. Her speed at the bottom is 5 over 2. Again, mass 20. G is 9.8. and her height here, 5 meters. We're doing these separately. I want to know how much energy she had at the bottom, how much energy she had at the top. If you calculate those, 5 squared is 25 times 20 divided by 2, which is really times 10. 25 times 10, you get 250 right there. 20 times 9.8 times 5 is 980. 250 minus 980, negative 730 joules. So how much heat did we lose? 730 joules of heat. We lost like the majority of our energy on this slide, actually, which might surprise you. You might be surprised at how much friction snow can give you if it's not packed down a lot. So friction did negative 730 joules of work. Again, negative energy means that energy was removed from the system and converted to heat, heating up the sled, heating up the snow, and that heat is eventually dissipated to the environment.